Chapter 13, Section 8, Exercise 4. We will find the critical points of this function f and use the second partials test to classify those critical points as relative extrema or saddle points. First, we solve gradient of f equals 0 by simultaneously solving the partial of f with respect to x equals 0 and the partial of f with respect to y equals 0. The partial of f with respect to x is the following. We set that equal to 0. We can isolate y. Now let's find the partial of f with respect to y. We set this equal to 0. Here is where I'm going to use y equals x cubed from the previous. We do this because we are solving simultaneously these two equations. Remember, you never divide by a variable. You could be dividing by 0 if you do that. We factor. So we have x equals 0, x equals -1 or +1, and these last two factors do not contribute any real solutions. Now since y equals x cubed, y equals 0, y equals -1, y equals 1. We have our critical points. The next thing we are going to do is classify those critical points. We use capital D, the determinant, or as I like to call it, the determinator. First, we will need to compute some second partials. So if the first partial of f with respect to x is 2y minus 2x cubed, then the second partial of f with respect to x would be -6x squared. At 0, 0, capital D, the determinator, equals this is -4, which is negative, implying that there is a saddle point at 0, 0. At 1, 1, capital D equals we get 32, which is positive. So we look at the second partial of f with respect to x at 1, 1. That is negative. Thus, there is a relative maximum at 1, 1. Very similarly, at -1, -1. We get positive 32. The second partial of f with respect to x at -1, -1 is also easily seen to be -6. So there is a relative maximum at -1, -1.